this video lecture, we are winding up with Riemann stages integrals section. Let's start with a recap to how we defined two equivalent rectifiable paths. If we are given two rectifiable paths, means they are both are bounded variation. Both of them are said to be equivalent to each other if there exists a function C from closed interval CD, which is the domain of the first path, to closed interval AB, which is the domain of the second path. And if the C is continuous and monotonically increasing, such that C of C is equal to A, C of D is equal to B, and sigma is equal to gamma composition C. So sigma and gamma were the two paths which were given. And usually an equivalence class, such a function will form an equivalence class of paths, and that is called a curve. And the trace of a curve is the trace of any of its members. We said how we define trace. Trace of a curve is nothing but the set of all points that are coming on the curve. Okay, so if we have a curve that will have a trace, and that trace will be the trace of any of the of members coming in them. That means any of the parts. Okay, if f is continuous on the trace of the curve, then integral over of f over the curve is the integral of f over any member of the curve. We are talking about the equivalence class of paths. So when we are talking about equivalence class of paths, we can just take any of the path that is coming inside that class. A curve is smooth, piecewise smooth if and only if some one of its representatives is smooth or piecewise smooth simultaneously. So hence we will not make the distinction between a curve and its representative. So that means an equivalence class is a curve. That means any of the path that is coming in that equivalence class will act as the representative. Okay, another important definitions coming there is, if suppose gamma is a function from closed interval a b to c, it is a rectifiable path where t is varying from a to b, then modulus of gamma of t b capital V of gamma colon closed interval a comma t. So this is nothing but the total variation we defined at the start of this section. That is, modulus of gamma of t is equal to the supremum of set of all summation k going from 1 to n modulus of gamma of tk minus gamma of tk minus 1 t naught t1 etc tn is the partition of closed interval at. And by the definition, modulus of gamma of t is equal to supremum of this set, right? So when t is made to increase in between A and B, definitely the set will increase. So supremum of a larger set will be tend to be larger, right? So modulus of gamma of t will increase with increasing t. Also, this modulus of gamma is a bounded variation, a function of bounded variation. And if f is continuous on the set of all points on the curve gamma, that is a trace of gamma, then we can define integral over gamma f modulus of dz is equal to integral from a to b f of gamma of t d modulus of gamma of t. So since we can define this f composition gamma here, because we treated f to be continuous on the trace. And if gamma is a rectifiable curve, minus gamma is the curve which is defined as minus of gamma of t is equal to gamma of minus t when t is varying from minus b to minus a. Also, it is usually denoted by gamma inverse. Okay. And if C belongs to C, gamma plus C denotes a curve defined by gamma plus C of t is equal to gamma of t plus C. So those are some basic definitions, and you can prove some basic results of the line integral which we defined, which are integral over gamma f is equal to minus of integral over minus gamma f. Modulus of integral over gamma f is less than or equal to integral over gamma modulus of f modulus of dz less than or equal to v of gamma supremum of the set of all modulus of f of z, where z is varying in the trace of gamma, and if c is a constant in the complex among the complex numbers, integral over gamma f of z dz is equal to integral over gamma plus c f of z minus c dz. So these can be proved as simple exercises. And theorem 1.18, you can just lecture it down, which is just an analog of fundamental theorem of calculus for line integrals here. So if capital F is the antiderivative of small f, you get the equality here, assuming the hypothesis given in the statement. So let's move on to lemma 1.19. This says that statement is given that G is an open set in C. Gamma is a function from closed interval AB to G. It is a rectifiable path, and F is a continuous function from G to C. Then for every epsilon greater than 0, there exists a polygonal path gamma in G such that gamma of A, this is capital gamma, this is small gamma. Gamma of A, capital gamma of A is equal to small gamma of A, capital gamma of B is equal to small gamma of B, and modulus of integral from gamma F minus integral over capital gamma F is strictly less than epsilon. So that is what we have to prove. So we prove it as two cases. The first case, we assuming that G is an open disk, and in the second case, as you can see, we treat G to be an arbitrary set, arbitrary open set. Okay, so in the first case, suppose G is an open disk, and we know that the trace of a curve is definitely a compact set. Trace means set of all points on the curve itself. Okay, that is a compact set. Definitely, it's compact because it's closed, right? Because its complement is open, so it's closed, and it is obviously bounded. So it's definitely compact. Okay. So you can see from the statement that this gamma is from closed interval AB to G. That means the curve is inside G. Okay. So suppose this is the curve. Okay, this gamma, and G we took it to be an open disk. So let it be the larger disk dotted lines here. Okay, that is G is equal to BCR with C center and R radius. Okay, so suppose C is somewhere here. Okay, and since this gamma, the trace is compact, we know that, and this open disk is open definitely. So there exists a portion here like this. That means some distance is made there. Like there is a space uh, in between the boundary and the set of all points on the curve. So suppose that be D. Definitely that is the least distance. uh, distance of the set of all points gamma from the boundary of G. That is definitely strictly greater than 0 because this trace is compact. Okay, we are assuming that G is BCR, then gamma is completely lying inside BCR, we know it. And next we are going to draw one more. This is open, and definitely there is a enough space in between the curve and the open disk we mentioned at first BCR. We are going to draw another open disk inside this open disk BCR, which is BC row, such that this gamma is in turn inside BC row. Okay, so that's what it's said here. We are constructing again a BC row such that this gamma is completely inside BC row. And what is this row? Row is nothing but if this was taken to be, see this, if the point, this is R, so call it, say if this is R, we know that there is a distance here. So we have to understand what this is. This is rho. So rho is defined as R minus D by 2. So D, this is D. If this is D, what we did is we take D by 2 and subtract it from R. So that will become rho. So definitely by the properties of compactness, we get that the such a possibility exists. So this B0 is drawn and gamma is inside it, and we know that this rho is R minus D by 2. So if this is D, this is nothing but D by 2. We are subtracting D by 2 from R. Now, if the function is given to be continuous from G to C, and it is continuous inside G, right? So we are considering the closure of this BC row, the smaller disk, and inside every and it is compact. Inside every compact set of continuous function will be uniformly continuous. So here in turn, F will be uniformly continuous in B0, the whole closure, and that is inside G. And without loss of generality, we can extend it to saying that F is uniformly continuous on G. Now choose delta strictly greater than 0 such that modulus of f of z minus f of w is strictly less than epsilon whenever modulus of z minus w is strictly less than delta. How can we say that? Because f is uniformly continuous. We can say that. Now, if gamma is from closed level AB to C, then gamma is uniformly continuous because gamma is on acting on a compact set, right? So it is uniformly continuous. So with that property, we can say that whenever uh, S and T, small s and T are very close, we can say that the corresponding images of those gamma S and gamma T are also very close. So what we are going to do is we are going to partition this closed level AB to such a smaller number such that corresponding images will also have the difference to be very less than smaller number, and that is we are taking it to be delta. Okay, so we made the partitions in such a way that S and T are very close such that the corresponding images, functional images with respect to gamma is strictly less than delta. Okay. And we know by the definition of integral earlier from the earlier theorem that modulus of integral over gamma f minus summation k is equal to 1 to n f of gamma of tau k into gamma of tk minus gamma of tk minus 1 is strictly less than epsilon where tau k is coming in between this tk minus 1 and tk. Okay. Now define a new function capital gamma from closed interval AB to C such that capital gamma of t is equal to 1 by tk minus 1 into tk minus t gamma of tk minus 1 plus t minus tk minus 1 into gamma of tk. Just substitute tk minus 1 instead of t capital gamma of tk minus 1 you get it to be small gamma of tk minus 1. Similarly capital gamma of tk you'll get to be small gamma of tk substituting it in this. Okay, and that makes us to infer that capital gamma of closed interval tk minus 1 comma tk is equal to closed interval gamma of tk minus 1 comma gamma of tk. That means this function is making out a straight line segment as an image from gamma of tk minus 1 to gamma of tk. So, and that happens to be inside G and that is a polygonal path since G is convex uh, and it's a disk. Okay. Now we are going to consider modulus of gamma of t minus small gamma of tau k. Okay, that is equal to modulus of capital gamma of t minus small gamma of tk plus small gamma of tk minus small gamma of tau k less than or equal to by the property of triangle inequality of modulus. You get like this, and we can say that this small gamma of tk minus small gamma of tau k will be strictly less than delta by 2 because this s and this tk and tau k they are coming from the partition which is very small. They are lying very close to each other. And talking about this capital gamma of t and capital small gamma of tk, you can get that from here. This gamma of tk minus 1 is here, the point is here, and gamma of tk is here, and capital gamma of t is a point lying inside this straight line. So definitely the distance between uh, capital gamma of t and gamma of tk will be strictly less than delta by 2, right? Because this tk minus 1 and tk are very close. So their functional images will be in turn very close as we discussed earlier. So we can say that the term sitting here is strictly less than delta by 2 and the term sitting here is also strictly less than delta by 2 and altogether we get that modulus of capital gamma of t minus small gamma of tau k is strictly less than delta for tk minus 1 less than or equal to t less than or equal to tk. Now, since integral over capital gamma f is equal to integral from a to b f of capital gamma of t gamma dash of t dt, which we said in the earlier theorems, okay, it follows that instead of this gamma dash of t, you can substitute uh, the value by finding the derivative of this gamma dash of t. And similarly, you can work out in the modulus of integral over gamma f minus integral over capital gamma f, and you can work them out as seen here. Simple steps. Okay. Getting that modulus of integral over gamma f minus integral over capital gamma f is less than or equal to epsilon into 1 plus total variation of v of gamma. It can be worked out like this. You can see the steps here, and also here you have to apply something. This f is uniformly continuous, we know it. So when this modulus of capital gamma of t minus small gamma of tk is strictly less than delta, we get that modulus of f of capital gamma of t minus f of small gamma of tk is strictly less than epsilon, since this f is uniformly continuous. So you get an epsilon from here less than epsilon from here, and what remains is integral over tk minus 1 to tk dt. So that happens to be tk minus 1 when we integrate usual integration, and you have a tk minus 1 in the denominator. You can cancel them out, and what you get is the term sitting here, the sum sitting here, and you can um, say that the difference, the modulus of the difference is less than or equal to epsilon into 1 plus v of gamma. And this epsilon is arbitrary, and this is a number. That means we are done there in the first case. And to prove the second one, G is an arbitrary set. We can look here. Here also this gamma, the trace is compact, and there exists a number such that there is this distance in between the points and the boundary. Choose a delta greater than 0 such that modulus of gamma of s minus gamma of t is strictly less than, or whenever modulus of s minus t is strictly less than delta. That is possible because this gamma will be uniformly continuous on closed level AB. It is already continuous on compact sets. It will be uniformly continuous. Now, if we are making a partition P for this closed level AB such that the norm of P is strictly less than delta, then modulus of gamma of t minus gamma of tk minus 1 is strictly less than r for t coming from closed level tk minus 1 comma tk. So the Kth part in the sense gamma k uh, coming from closed interval tk minus 1 to tk. Okay. That will be contained inside the open ball b of gamma of tk minus 1 comma r with r radius. So and the gamma k, the function can be defined as gamma k of t is equal to gamma of t. Then you have the trace of gamma to lie inside the same open ball, what we talked about for k varying from 1 to n. So the gamma can be made into parts, n parts. Okay. So which leads to a situation that makes us to apply case 1. Okay. That means there is a polygonal path capital gamma k from closed level tk minus 1 to tk uh, to the range, the open ball B sitting here such that capital gamma k of tk minus 1 is equal to small gamma of tk minus 1 and capital gamma k tk is equal to small gamma of tk, and that means modulus of the integrals is strictly less than epsilon by n here because we have splitted it into n uh, partitions in parts. Okay, so uh, we can at the end define capital gamma as the union of all the n parts we formed for this capital gamma, and that will make us end at the desired polygonal path. So that's an outline how to prove theorem 1 point lemma 1.19. And there are some remarks there which you can read out. And also we know what a curve gamma from closed interval AB to C is said to be closed if the initial and the final points are the same. Gamma of A is equal to gamma of B, and you have a corollary to read which says that if G, gamma, and F satisfy the same hypothesis as we said earlier, then if gamma is closed, then integral over gamma F is equal to 0, which you might have seen as the Cauchy-Gauss theorem while we were doing the degree program. And also there are some inferences here which you can read out, which includes the Cauchy-Riemann equations, which we have already done, and do work out what this example says to us, and the function is f of z is equal to modulus of z square. Um, we are making an inference out of the function using the theorem which we stated. So that's the end of this section. So thank you for watching our video. See you in the next video lecture.